100, 10 to 50, you go lower.
I said it was a half-life of 10 years, so we're going up by 10 years in time each time. And each 10 years that passes, this gets cut in half, the amount.
Oh, I see. Okay, never mind.
Amanda.
No, so the model...
I'm actually not done with this equation yet. So that if that was your question. Let me finish this equation and then take math questions.
What does initial mean? What do you mean by that?
Initial amount. We started with 100 pounds of this stuff.
So is that what you're going to put in there?
Yes. Now, here's the deal though. Because it takes 10 years for this to go down by half, we have to put an exponent up here that takes that into account.
So would you put 10?
Exactly wrong. We're going to put t in years, but exactly wrong is good. You're on the right track, actually. We put t over 10.
Then what's a 10?
Because 10 years have to pass for this exponent to be 1, and an exponent of 1 will mean 1/2 multiplied by it. 20 years will have to pass for this exponent to be 2, so that this will be 1/2 and 1/2 again, which will get us down to half of 100 and then half of that. 30 years will have to pass for this exponent to be 3. Yeah. So if it takes a certain number of years for something to happen with exponential growth and decay, you put your time up here and you divide by that number.
And it's always 100. In this case, it's always 100 for the initial.
Yes.
Okay.
Now, if I start with 75 pounds of selenium, then I've got a different model, and I have to put 75 in here. But this would still be 10 for the same element. Yes, Amanda?
When you take, like, t is the time.
Yes.
So do you plug in, like, 20 divided by 10 is...
Yeah, well, these, I mean, if it's a nice half-life like this, we start with a nice amount. You can do most of it with a chart, maybe even faster. But what if I need to know, for scientific reasons, exactly how much selenium there is in 32 years? Okay, in between the half-lives, in between the 10 years, that's really a pain. That's where I put this in my calculator, and I put 32 in for t, and I'll get some horrible decimal. Okay? Now I need to go over what this looks like. Is there a question I missed anywhere in this example? Dimi?
Can I go bonus?
Yes, Arturo.
So is it possible to get rid of radiation?
There are supposedly ways to scrub it, but I don't know if they're 100% effective. There are ways to clean it up.
I don't think anything is really...
Now, cadmium dampens nuclear reactions, but I'm not sure how. Cadmium is another element that like absorbs radioactivity somehow. It's a great question for a chemistry teacher.
Wait, this row.
Yeah.
Well, it's kind of random, but it has to do
Real
with
quick.
clouds and all.
Okay.
Have you heard about the volcano in Iceland that stopped like all
Yes.
air travel?
Yes. That's like Mother Nature just saying, we don't want you flying anymore.
Have you heard about the snakehead fish?
Yes. Okay, but now, let's go back to the math. Okay, Sarah, follow me over this way. Okay.
Land, but it has like insane, awesome teeth.
No, that's not.
Okay.
It's cool, but it's not good.
Now, graphing these. Okay, I'm going to graph two examples. Okay? I'm not going to graph this one yet because that's a little complicated. My first example is just going to be y equals 1/2 to the x. Okay? Y equals 1/2 to the x.
Wait, you just did that.
Well, I'm not going to graph that example, but I'm going to get back to that. Y equals 1/2 to the x is similar to our exponential growth models, but here's what's...
that's like the parent function.
Yeah, exactly. This is the parent function to this, and I'm only going to worry about the parent function for a minute. God, thank you, Amanda. You're on today. I love it.
Sorry about your door.
Sound like you broke.
Yes, Mimi. The tragedy is that I'll have to walk over here now. All right, I'm running out of time, and I got to finish this one. As interesting as talking to Mimi about the door is. I am still interested in the same 3 points, -1, 0, and 1, to get my general idea of the parent function's behavior. However, this gets a little bit more tricky. What is 1/2 to the -1 power?
-1/2.
2. Very good. Remember, Nimi, negative exponents have nothing to do with positive or negative sign. I realize that's annoying, but it's true. Anything to the 1/2 power makes a reciprocal, so that's going to be 2.
Oh.
What is 1/2 to the 0 power?
2. 1.
1.
No.
Anything to the 0 power is 1.
Can you...
But you said it'd be the reciprocal.
If it's negative.
If it's negative, it's the reciprocal.
Then when
If you
if
have a
it's
negative
positive.
If it's a positive exponent, you do what you've been doing with exponents since, I hope, middle school.
I still don't get why it's
negative or
2.
positive.
Okay, let me show a step here.
Different.
Remember when you have... Okay, hang on, guys. I'm working this one out. Remember when you have an exponent and a fraction, you can apply the exponent to the top and the bottom, right?
No.
And then remember, well, guess what? You can.
No, because
Now
you
remember
have to
Phil's rule, Sarah. Of Phil's, it was not really. It's the mnemonic. Remember the rule. Flip the line, change the sign.
Cross the line.
Cross the line, change the sign. So if you have a negative exponent on the top of a fraction, it becomes a positive exponent on the bottom. If you have a negative exponent on the bottom of a fraction, it becomes a positive exponent on the top. 2 to the first is 2, 1 to the first is 1, 2 divided by 1 is 2.
Okay.
The shorter version is, if you have a fraction and the exponent is just negative 1, okay? If it's a negative 2, flip it, then square it.
Flip it.
Flip it. You gotta say it like that
Flip
too. You gotta flip it. Okay,
It's like
but
the camera.
now 1/2 to the 1, what's anything to the first power?
Itself.
itself.
Itself. So
25.
this is going to be 1/2. How does this compare to our exponential growth 3 points?
It's backwards.
It's backwards. How do you think the graph's going to look?
Backwards.
Backward. So it's
Clever
like
kids.
reverse ballerina.
Well, they're not ballerinas anymore, but yeah, it's kind of like the difference between ballerina and reverse ballerina. That's a really good comparison, actually. So my 3 points of interest, instead of being what you graphed earlier this week, 1/2, 1, and 2, my 3 points of interest are now going to be 2 up here, 1 here, 1/2 down here. We start up high like this.
I can't see.
I'll have to move in a moment then.
Thank you.
So we start up here like this. We label our points for maximum clarity. And instead of having an airplane taking up and accidentally going vertical and hitting stall velocity and crashing, we have an airplane coming down into a nosedive,
And this
managing to
time-
pull it out and landing safely.
I can't see.
We could compare it to the space shuttle.
Yes, we could compare. Well, actually, the space shuttle apparently has to skim the top of the atmosphere to slow down.
Really?
So it like almost does like a full orbit before it starts entering the atmosphere and landing.
That's
I
lovely.
didn't know that.
Is
it's,
this what our homework's like?
Apparently, it goes like it skips like a rock on a lake as it enters the atmosphere. If it went straight down into the atmosphere,
They would burn up.
probably yeah.
Yeah.
But yeah, this is like a plane taking forever to land. I have felt like this. Flying makes me nauseous. It's not a fear of flying. I actually pray for the plane
the
to
roller
explode
coaster makes
after
you
about 10
nauseous
minutes.
too.
But yes,
Wait.
no, they're fine. But a plane landing is. I mean, I feel like this because this graph is getting closer and closer and closer and closer to the x-axis. This is still an asymptote without ever reaching it. Okay? Stop. Now, it keeps getting closer and closer. This is the math model. It's not a perfect model. Mathematically, this never reaches the x-axis. If we're really using this to model something like exponential decay, there is a magical moment when the last atom actually transmutes. Might take a long, long time. That'll be stuck in my head all day. Thanks, Sarah.
You're welcome.
Now, come back over here, and I'm going to graph the same thing. I shouldn't have said that. That was, I just gave away the trick. Okay,
So
now,
now you have to take the parent function and add the.
yes, now I would, but we're not going to worry about that too much.
Why did you just erase all that?
Because we're doing something, we're going in a different direction now.
Great.
Y equals 2 to the negative x. Y equals 2 to the negative x.
And the same 3 points.
Same 3 points. Yeah, let's start by plugging those in.
0, negative 1.
Yeah, negative 1, 0, 1. Okay. What happens when I put negative 1 in for negative x?
Positive 1.
Positive. So this is 2 to the positive 1.
Is
So
this
that's
a new
2.
one?
Yeah.
Why
What
is it always
happens when I
2?
put... Yes, that's 2. What happens when I put 0 in for the negative x?
1.
2 to the 0, which is 1. And what happens when I put 1 into the negative x?
1 over 2.
2 to the negative 1.
2 to the negative 1, which will make
1/2.
1/2. Notice anything similar between these points and those points?
They're the same.
Yeah, they're the same.
They're the same. Okay, good. Here's the deal. Exponential decay can be expressed 2 ways, and they're both equally valid.
Just like Becca eats 2 M&Ms for every 1 Mr. Valvo eats, and Mr.
Yes.
Valvo eats 1 for every 2 M&Ms.
Exactly, like inverse functions.
Oh, how about?
Sort of. Sort of. There's a slight difference, actually.
Except these will show up the same way on the
I
graph,
don't
whereas the other ones...
Very smart, Phil.